Hi guys, welcome to lesson 7.7, Exponential Growth and Decay. Our objective for this lesson is that I can model exponential growth and decay. Our essential understanding is an exponential function can model growth or decay of an initial amount. And the way we do that is by using the exponential growth or decay formula. And it's basically the same formula and we just name it a couple different things. So, x is always going to be our independent variable, and y is always our dependent. All right, now exponential growth can be modeled by the function y equals a times b to the x, where a is greater than 0 and b is greater than 1. The base is the growth factor, base b, growth factor, which is equal to 1 plus the percent of the rate of change expressed as a decimal. All right, so b is our growth factor. So that is how much we're increasing by every single time. And a is our starting amount. Okay. All right, so now modeling exponential growth. So we're going to use that basic formula to solve this problem. So suppose that in 1985, there were 285 cell phone subscribers in a small town. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were in the town in 1994? And then write an equation to represent the number of cell phone subscribers after X years. So we're actually going to start with that first step. We put our independent variable, or dependent variable, y, is equal to our starting amount, which is what we start with, 285, times our growth factor. So we're growing 75% per year, and we said it was going to be 1 plus the percent rate of change as a decimal. So 75 is 0.75. 75% equals 0.75. So 1 plus that, 1 is 1.75. The 100% of the original plus an additional 75% for the growth. And we're doing that to the x power, because x is our number of years. So now we need to plug in our goal, which is 1994. Well, from 85 to 94, 9 years have passed. All right, so that's going to equal 9 years. So we are subtracting. So it's kind of like that water tank problem in a way. So y equals 285 times 1.75 to the 9th power. And you just type that into your calculator, and you get y is equal to 43871.99, or approximately 43,872 subscribers. Okay, so that's approximately how many there would be after 9 years. Okay. Oh, and just for the record, that was my first cell phone from a company called Primeco. Doesn't exist anymore. Anyways, all right. The population of deer in a region was 3,500 in the year 2000. So that sounds like a starting amount. Since then, the population has grown by 3.5% annually every year. What will the approximate deer population be in 2020? Write an equation to represent the increase after X years. So again, y is equal to our starting amount, 3,500, times our growth factor, which is 1 plus 3.5%, or 1.035, and that's to the x power. So we plug in, we want to know from 2000 to 2020, that is 20 years that have passed. 3,500 times 1.035 to the 20th power. And when you evaluate that, you're going to find that y equals 6964.26, or approximately 6,964 deer. Okay? All right. Question 2 is going to be dealing with compound interest. Now, compound interest is going to be calculator heavy, and there are a whole bunch of parts to it. Now, we will give you this formula, but I'm not going to give you the key of what each of the letters are. I will just give you the formula. You need to know how to apply it. So compound interest is when a bank pays you interest on both the principal, the amount that you initially deposited, and any interest that you've already earned. So every month it pays you the interest, it goes into the account, and now that is being used to calculate the interest for the next month. Simple interest, which we did a couple chapters ago, that is just a fixed amount of interest per year, and it's based on the amount that you initially put in. So compound interest is a little friendlier to your wallet. All right, so A is the balance, how much money we have in our account at the end. P is the principal, that's the amount of money that you initially deposit into the account. R is the annual interest rate written as a decimal. N is the number of times interest is compounded per year. How many times are they actually going to add the interest in? So that goes there and there. And then T is the time in years. How long has this passed? All right. So suppose when you were first born, your parents deposited $2,000 into an account paying 4.5% interest, compounded quarterly. What will the account balance be after 18 years? What would the account balance be after 18 years if it was compounded monthly? So we're going to do two separate problems here. So let's just fill in the information that we have in our problem. A is equal to our principal, the amount we deposited, $2,000, times, parentheses, 1 plus the rate over the amount of times interest was compounded. So our rate is 4.5%, so that's 0.045. And we're compounding it quarterly. So that means 4 times per year. And it's being raised to the n, number of times that we're compounding it, times 18, how many years we are going to keep it in the account. Now, when you go to type all this into your calculator, there are a couple things you need to be very, very, very careful of. The first one is, and I'm going to put it in red here, you need to make sure you put this in parentheses. Because if you don't, you're only going to raise it to the 4th power, and then you're going to multiply your answer by 18, and you're going to get a much, much larger number than you want to get. So the way I do this is I would have, type into the calculator, 2,000 times 1 plus 0.045 divided by 4, close those parentheses, raise it to the 4 times 18, close the parentheses. Oops, I need parentheses there. Insert parentheses. So your exponent needs to be in parentheses. Now, if you wanted to do 4 times 18 first and then just type in that number, that is fine. That'll get you to the right answer. But if you don't have, if you just typed in 4 times 18 without parentheses around it, you would do to the 4th power times 18, which gets you a radically different number. So parentheses are going to be your friends for this unit. So you hit enter and you get 4475.53. So our balance is equal to $4,475.53. Okay, we need our units. Now, if we're going to do this for compounding monthly, we're going to set up the same equation. A equals 2,000 times 1 plus 0.045 over monthly is going to be 12 times per year. And we have 12 times 18. So we do the same thing with our calculator. 2,000 times 1 plus 0.045 divided by 12 this time. And we are raising that to the 12 times 18th power. So we find that A is equal to $4,489.01. So, oops, 89.01. Okay, so you can see it's not a whole heck of a lot of difference, whether it's being compounded quarterly or monthly, when you're talking about 4.5% interest. Now, if interest were quite a bit higher, you have the potential to make more money than that. Okay. All right, so Michelle invests $8,000 in a money market account that pays 3.25% interest compounded monthly. How much money will be in the account after 12 years? So we start that off, same thing. A, our amount in our account is equal to 8,000 times 1 plus, we've got the interest, 0.0325 over, we're compounding it monthly, so that's 12 times a year, to the 12 times 12. So type it all into your calculator, hit enter, and you find that after that amount of time, she is going to have $12,168.25. Okay. You guys try letter C on your own, and then I'm going to go over the answer. So A is going to be equal to, you opened a savings account that pays interest bi-monthly at a rate of 4.75%. You initially deposited $15,000 into the account. What will the balance be after 15 years? All right, so our starting balance is 15,000 times 1 plus our interest rate was 0.0475 over, I said bi-monthly, so that means every other month, so that'd be 6 times a year, to the 6 times 15 power. Calculate that out and you will have $30,500.55 from that initial $15,000 investment. Okay. Last section in 7.7 is exponential decay. Now, the difference here is that we are decreasing instead of increasing. So it is modeled by the exact same base function, y equals a times b to the x, except this time a is going to be greater than 0. Again, our starting population has to be greater than 0. And b has to be between 0 and 1. So this is going to allow us to be decreasing. The base is our decay factor in this one, and it is 1 minus the percent rate of change expressed as a decimal. So we have decay factor instead of growth. This is still our initial amount. This is still going to be our independent variable. And this is still our dependent variable. All right, so now we just need to go and figure out what we're starting with and all that. All right, so the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases by 11.5%. What is the approximate pressure at an altitude of 5,000 meters? So we start off our equation with our dependent variable, y. is equal to our initial amount, which we said at sea level is 101 kilopascals, times our growth factor is we're decreasing by 11.5%. So we have 100% to start with. We decrease by 11.5%, and we divide that by 100, and we get 0.885, or if we did 1 minus 0.115, we get 0.885. So that is our base. That is our growth factor, or decay factor. All right, so it's 0.885 to the x power. Because every single time we go up 1,000 meters, we decrease 11% from our starting point. Now, we also were asked what is the approximate pressure in an altitude of 5,000 meters. So we said every 5 meter increase, so that is a 5 increases. We went up 5 levels in the atmosphere. Okay, so y equals 101 times 0.885 to the 5th power. So y is going to be equal to 54.83 kilopascals. All right, and kilopascals is the unit again. Okay. All right. Second one, a unit of measure that we're a little more familiar with, population. So the population of New Haven, Connecticut was 148,200 in 2005. Since then, the population has been decreasing at an annual rate of 2.9%. If this continues at this rate, what would the population be in 2015? So we start off, y equals our starting amount, 148,200, times our annual rate. So we've got 1 minus 0.029, and it is 0.971. So times 0.971 to the x power. So this is saying our initial population, we're going to multiply it by 97.1%, because that's how many people are going to be left every year. This is going to give us an equation, or a number that is how many people are left. So we have 148,200 times 0.971, and we're going from 2005 to 2015, so that is 10 years, so to the 10th power, and y is going to be equal to 110,418 approximately people. So approximately 110,418 of the 148,200 are going to still be there 10 years later, if this trend continued, which it doesn't necessarily. Okay? All right. That is the end of the notes for this lesson. Make sure you fill out your level of understanding. Rate yourself from 1 to 4. Again, be honest with this. Write down any questions you may have come up with as we went through this lesson, any confusions you may have or things you want clarified. And then lastly, make sure you write your summary. Describe how, maybe teach somebody how to set up a problem that is representing exponential growth or decay. Okay, there you go. Have a great night.